film my presentation here and enter the extra symposium. And as Professor Salvador has given us a introduction for the micro nano robots, and now I'm going to talk about a version of many micro and nano robots, one of the emergent behaviors that comes out from this group. And my presentation is titled with a three-dimensional reconfigurable microrobot swarm that is as an inspiration from schooling fish in nature. My presentation is going to give you in the following 5 parts. And the first, let me introduce what is the swarm behaviors for the micro nano robots. So the swarm behaviors in nature is ubiquitous in nature, such as the bird flocks flying in the sky form its aerial pattern, schooling fishes creating underwater vortices, and this is keep it underwater rotating structure. That many weaver ants establish bridges. They connected cooperatively for cargo delivery or transporting food, and these small fishes swim cooperatively in the group to avoid the big predator. The big fish in the corner to form a cavity here to avoid the predators. These strategies has proven us 1 + 1 could be greater than 2, and the cooperation between the individual agents, the individual animals, or individual micro nano robots is really important for the emergence of such small behaviors. That has 3 advantages. Such working mode is efficient because of it's composed of a large amount of individual agents, and the system is robust. Even some individuals lose their functionalities, and the whole group is sorry, for the control bit. The group is adaptability is great because we can transform the structures, and adaptability is preferable for the conducting on-demand tasks. The performance has been revealed in a video. You can see that this individual videos is just like showing in the video. These individual micro nano robots with the others, there will be something more interesting happens. For connecting in the whole group. And some behaviors will be similar for what we have done for the collective behavior of micro nano robots. Transformation. Migration and transportation. These behaviors are we're gonna do control the micro nano robots to perform. Currently, no matter it is a biological system or a bionic system, the currently studied swarm behaviors are mostly implemented on 2D boundaries. These equally cells can perform an ordered pattern and the trajectory of elliptical using the tracing particles. And these magnetotactic bacteria can be guided to construct a micropyramids. For the abionic system, we can control the external stimuli to perform the reversible patterns such as dispersion and aggregation. This elongation and shrinkage of the micro nano robots. We can use the composite of micro nano particles. On the other, these swarm behaviors is implemented on substrate. We are always used to study some phase transition, some transformation of the swarming patterns like oyster-like aggregation, collective migration, and different modes, such as ribbon-like, the dispersed particles of multimodal motion. On the other side of the 2D boundary, it will be the liquid air interface on the surface of some specific liquids to perform this ordered pattern, and this can be constructed for our pre-assigned patterns or crystallization process. They can assemble some functional patterns such as snake-like structure to transport a cargo for encaging and transport many cargoes on the liquid air interface. But I'm going to focus on the 3D motion. Why 3D motion is important? because the 3D motion or 3D patterns of the swarm behavior will introduce a lot of more contact with the structure for improving the catalytic performance. And these behaviors of vertical motion can be easily controlled using a strategy called buoyancy force, controlling the bubble generation on. And the electrical field can also be used to control the vertical motion of these particles. So the vertical motion of the individual particles is important. And another light-driven, these particles can be reoriented and get focused directly to conduct the vertical motion. And collective behavior is only implemented in this theoretical work, but for performing a comet-like swarm. But this is only theoretical work and not practical implementation for the many agents. But what I have done is to realize it in experiments. As inspired by the schooling fishes, those two pictures are taken by a photographer in Sudan of schooling fishes. I have created a microswarm tornado composing of these four stages: the rising, hovering, oscillating, and landing stages. Particularly for the oscillating stage, where I will talk about for the functionalities with this microswarm. So first, I need to construct a two-dimensional microswarm. The microswarm is implemented for the combined source of magnetic field and the optical laser irradiation. The optical path goes through this laser path and illuminated on samples. The magnetic actuation is used to construct a 2D microswarm on the substrate, and the laser irradiation introduced the third dimension. I use two parameters to describe this microswarm because it has to be stable and compacted for this further lifting, because there's no support from substrate. Otherwise, the microswarm in 3-dimensional will be inclined or even fractured into two or three fragments. This is not favorable. So the magnetic field and the laser field has to be finely coordinated. And the laser field comes to the swirling of the microswarm. The laser radiation goes to give a laser profile illuminated on the particles, and these particles will aggregate together toward the center using such active convection, and even lifting these particles, providing a third dimension to construct a 3D structures, a tornado structure. Sorry for the drift. The reconfigurable, here is reconfigurable the whole generation of the microswarm. The inner circle of these images are the top view of the microswarm tornado, and the outer view are the side view. You can see these magnetic nanoparticles are start from the initial states dispersed on the substrate and lifting like a tornado pattern to the 3D structure under the laser radiation and rising to this structure, and even it can maintain the hovering for more than 5 minutes, which is really long and stable for such kind of structure. And therefore, later I introduced a oscillating stages. They in different planes, in the vertical plane of the XY plane and the YZ plane, accompanied by the landing back of the microswarm back to its initial state. The whole generation is reconfigurable by evaluating the surface area on the substrate is reconfigurable, and they use this periodical motion. The rising state of this microswarm can reach around 800 micrometers, and the microswarm can be controllable as a specific head reversible. The microswarm tornado not only has a tornado pattern, but also has a tornado characteristic. It has commonness inside of the tornado. So I use the degradation of methane blue to show the correct characteristic of this microswarm. When I implemented the microswarm in the initially degradation of methane blue, if we don't implement the microswarm in the E-reaction, it will degrade it to be transparent. But when I implemented this microswarm in the E-reaction, you can see there a lot near space is trapped for the substance around the materials. This velocity region cavity has also shown us that there's a near region for trapping the substance around, and then maintain the commonness for the methane blue is trapped and not degraded by the normal degradation effect of this chemical reaction. To quantitatively evaluate such behavior, And I evaluated using the UV absorption of the near region microswarm and the far region microswarm. You can see at different regions, at the different regions in the chemical reaction, there's always a gap between the far region and the near region of the microswarm tornado. And this gap becomes larger and larger, means the trapping effect and the materials trapped are become more dominant. Then why? Then here comes we trapped something, then what we want to deal with further. And here comes to the oscillation state I introduced to release the trapped methane blue. By comparing the oscillation samples and without oscillation samples, we can see there's a little bit gap for 1 minute treatment, and that the releasing gap of the methane blue is obvious more dominant using a 2 minutes microswarm tornado or using the oscillation state. So it means, so here the methane blue trap has been released on demand by controlling the oscillation stage. Finally, let's review the whole generation of this microswarm tornado. Starting from the initial state on the substrate, it becomes rising up the tornado pattern to maintain and hovering in a 3D space and maintain it. The structure is really stable and it can maintain a long time. And then the oscillation stage comes to release the trapped substance here. And you can see this microswarm is lands back, and this surface area on the substrate becomes larger and larger, and the microswarm will come back to its initial state. The whole process is periodic, and we can just reprogram the magnetic field and balance its position with the optical field, and the whole structure can be reconfigured. And the microswarm tornado is generated again safe and sound with the property of anti-gravity mass transportation, reconfiguration, a 3-dimensional collective behavior and pattern is constructed, and also the tornado characteristic inside the calmness. So lastly, I would like to thank my colleagues and many useful suggestions from the professors for helpful discussions, and would like to thank Professor Liu for the organization of this excellent symposium. Thank you for your attention.